16.6 Parametric surfaces. To study the integration in dimension, sometimes we want to integrate over a surface, like in this graph. Sorry, y, this is z. We have seen that the area of a surface is written in this way: 1 plus v prime x squared plus 1 plus v prime y squared dA, and A is the projection onto the xy plane. If the equation for the surface is written as z and function of x and y, right? However, it's not the most convenient representation of a surface sometimes. For example, for a sphere, like that, then, well, you can write on z as 1 minus x squared minus z squared, y squared. But if you want to integrate, you could probably prefer the theta phi coordinate, right? Then you can write on the points on this sphere as let's say x, which is let's say rho equal to 1, okay, the radius equal to 1. So this would be sine phi cosine theta, sine phi sine theta, and cosine phi for x, y, z. So we can use theta phi to parameterize a spherical surface instead of x, y, and z. Just like a curve, right? For a curve, you may write on this as y as a function of x, or you can write on x as a function of p, y as also y is a different function p, like that, right? So that's called a parametric curve. And we can also parameterize a surface, but you need two parameters because it's 2D. For example, we can use theta and phi, right? And in general, we can use two parameters. Let's call them u and v. So then u and v will give you a function. So the points on the surface is defined as a vector function of u and v. Or you can say it as x uv, y uv, and z uv. So each uv will give you a point, and if you change u and v, you will get a 2D surface. So let's see what will be this. Let's give one example first. So 2 cosine u v 2 sine u. And what kind of surface is that? Well, you notice this part. So we have x squared plus z squared equals 4, right? And y is independent, so y is arbitrary. So that means it's on a circle with arbitrary y, so it's a cylinder. And y is arbitrary, so it's like that, right? So it's a cylinder along the y-axis. Okay. And let's see what is z squared plus r minus a squared equals b squared. Well, r is that r theta, polar coordinate r. So how do you parameterize this? If you write on v, so what is this? Okay, let's take a look. Let's say z x. Okay, let's say y equals 0. So this x, this is just a. R is just x. So this is a circle, right? Centered at A0 and the radius is V. And then x becomes r. It means you have to rotate this about the axis. See what you get? You get a torus. So that's what you get by rotating a circle around the z-axis. And how do we parameterize this? Well, xyz wouldn't be convenient because, it's just not so easy because r equals x squared plus y squared square root, right? It's awkward. So we can just say use this is theta, right? So you can see z equals b cosine theta, and r minus a equals b sine theta, right? And then this r equals r equals a plus b sine theta, right? Then, I shouldn't use the symbol theta. Let me just call it the alpha. Alpha. Not this one. This alpha. This is still theta. This is alpha. Cosine alpha, sine alpha, like that. So you have z equals b cosine alpha, and r equals a plus b sine alpha. And theta is just the polar coordinate. So the easiest way is to use cylindrical coordinate. And you don't say what is xyz, you say what is z r theta. And in this case, theta is just theta. And z and r are written as a function of alpha. So our parameter is alpha and theta. Right? Then you can convert it into z r theta. And then in turn, you can write down what is z x y. And x is just r cosine theta, y is r sine theta. And you can plug in this into your r. Right? So you have two parameters, alpha and theta. And you have a surface. Okay. And also we have a parameterization for a sphere, which is using theta and phi. Alright, now we have seen quite a few examples. Let's do some calculus. So suppose we want to integrate over this surface. And let's plot this surface using u and v. So this point here, it's r as a function of u and v. Right, and this line here, this curve here, is sort of u-axis, which means this is r with a little bit changed u, and this is a changed v. Right, so this is like a changing v, this is changing u, and this is changed both. So this will be r of u plus du and v plus dv. Okay. So now look at this region. If du and dv are both small, then this is like a small plane. Well, actually it's more than a plane, it's just a rectangle, non-rectangle. In general, it's a parallelogram. It's not necessarily a rectangle, because the angle may not be 90 degrees. And what is this? This is about Ru times du. And Ru means the derivative over u, right? And this is Rv times dv, right? Because you are changing only in v with u fixed. So what is the area of that? or we can say the surface area. Well, we can obtain it using this method. R u du cross R v dv. Do you remember what this gives us? It'll give us a vector in the normal direction, right? Perpendicular to RU and RV. And this will give you a vector that is the normal direction and the surface area. So the cross product will give you a vector in the direction of n, and the size or the length of this vector is the surface, or you can say the area of the parallelogram. So we can integrate the area. So you want total area, just integrate over ds, right? And how do you find ds? ds is the norm of this vector, because it's a norm of that vector, right? N is a unit vector. So you will just get the norm of Ru cross Rv cross Rv and du dv. Alright, so you find out the derivative over u and v and take a cross product and take its norm, then integrate over u and v. And you need to specify the limits for u and v. Alright, so that's how you find out the area. And let's see an example. Say we have a sphere. Alright, so as we said earlier, we can just use theta and phi, and suppose the radius is 1. So you will have the parameterization. R equals, let me write again, it's sine phi cosine theta, sine phi sine theta, and cosine phi. Alright, let's find out the surface area. Let's take Ru first. In this case, it will be r theta. So take a theta derivative, and you will get sine phi sine theta, and sine phi cosine theta, and then this will give you 0. Remember r phi would be cosine phi cosine theta, cosine phi sine theta, and negative sine phi. Alright, let's take a cross product. So, you can just do this, right? So you get negative sine phi square cosine theta, and do this, and this one first give you 0, and that one give you positive, then it's negative sine phi square sine theta, and the last one will be this. Oh, what is that? So you have a negative sine phi cosine phi times sine square, then minus cosine square, and sine square plus cosine square equals 1. So that's okay. All right, now let's take its norm. So the square root of all together. So the first is sine square phi cosine theta squared, sine square phi sine theta squared, and sine phi cosine phi squared. It's kind of complicated, but hopefully it's not too bad. So you have cosine square, sine square, it's gone. So you still have sine square, and square again gets to the 4th, and then you have this sine square, cosine square, right? So you can factor out the sine square and take out, you get sine phi, and inside you get sine square with cosine square, which is 1. Take a square root, still 1. Okay, that's what you get. Not bad. Alright, finally we'll get this, and let's see what you get. So the total surface area is, remember what it has? You have this term times d phi d theta, right? You know. So you have this term. Oh, that's sine phi. D phi d theta. Ah, does this look familiar? That's exactly what we learned earlier, right? And phi equals 0 to pi, and theta equals 0 to pi. And then you can integrate this, which will give you 2, and then 2 pi, so you get 4 pi. And the 4 pi r squared equals 4 pi because r equals 1. So that confirms what we already know. Okay, now let's do something new. How about let's try something like this. Okay, suppose you have u square uv 1/2 v square. Okay, that is a uv parameterization of a two-dimensional surface. And let's say we know the dimension, the domain of u is 0 to 1, and v is 0 to 2. It's kind of hard to sketch it because these functions are not linear. So let's forget about the sketch, just try to find out the surface area. Okay, so remember what to do. You have a du dv, and u is from 0 to 1, v is from 0 to 2, and inside it's cross product of the derivative, right? U derivative equals u v 0. The v derivative would be 0 u, no, this is 2u, and this is v, right? So what do we get? Okay, 2u v 0 0 u v, right? Yeah. So that way you get this one equals v square. Then this way you get 0 minus that negative 2uv, and this way you get 2u squared. Okay, right, that's what we have. So then you have square root of everything square, v fourth plus 4u squared v squared plus 4u to the fourth, and then you have du dv. Well, does that look good? Actually, not bad, right? This happened to be, we're kind of lucky. So you have 2u squared plus v squared, and if we square it, you get v to the fourth, 4u to the fourth, and 4u squared v squared. Huh, that's, and take a square root, it's gone. Alright, so then we can integrate. That's pretty easy. So you get dv, then you get when you take integrate for u, you get 2/3 u cubed plus v squared u from 0 to 1, and you plug in u, so you get 2/3 plus v squared, right? Then you get 2/3 v plus 1/3 v cubed, 0 to 2, and then you have 4/3 plus 8/3, and that is 4. Oh, finally. So we get this area. Okay, so we know how to find out the area of a parametric surface. And of course, in the simplest case, that your parameter is just x and y instead of u and v. Then your ru cross rv is particularly simple, because that means it's 1, 0, 0 and 0, 1, 0, right? Because this is just x, this is just y, right? So, oh, sorry, my bad. This is not 0. This is zx, this is zy, because z is not a constant. Z is a function of x and y. So then you have this part, zy, then you have this part, then you have sorry, that's negative dzx, then you have a negative zy, and then you have a 1. Right, then what's the square, what's the norm? The norm would be v 1 plus zx squared plus zy squared. And that's what we learned earlier, right? So surface area equals 1 plus zx squared plus zy squared dx dy. So that's not new, right? That's something we know already. Okay, so one last question. Suppose you have a given parametric surface like that, and let's say we pick a point 1, 2, 2. Let's find out the tangent plane to this surface. How do you find out tangent plane? You find out RU, RV, then take cross product, get this N, right? And if you know the point along with this N, then you can write on the plane, right? The plane is just this, R minus R naught. You know, this is a naught, R naught, times this N equals 0, right? And what is this N? N is just RU cross RV. But you have to evaluate at this point, right? Okay, so let's do it. So what is the RU RV? It will be 1, 0, V cross V derivative 0, 1, U. And you have to plug in U equals 1, V equals 2. So that means 1, 0, 2 cross 0, 1, 1. Right? U equals 1, V equals 2. And what is that? IJK 1, 0, 2, 0, 1, 1. So you get, just be careful. Okay. 0 minus 2, and so you get 0 minus 1, and last one is 1 minus 0. Okay, so that's your n. Well, that is the n times the area, but we don't need to worry about the area itself because we only care about the direction. So R0 equals 1, 2, 2. So the formula would be x minus 1, y minus 2, z minus 2, dot, negative 2, negative 1, 1 equals 0. Well, if you want, you can write down negative 2, x minus 1, minus y minus 2, plus z minus 2 equals 0. Right? So that's your tangent plane. Okay, I think that's it for this section, and see you next time.